All right, welcome everyone. We are working on in-class problems, 2D motion in-class problems that we got last week. Looks like this. We're going to go through problem number 3 together. So, it says what velocity, there's some wording issues, grammar I need to fix. Sorry, I apologize in advance. I'll just kind of make it sound like I kind of want it to sound. With what velocity will a daring duo cruising in a shopping cart towards a 1.5 meter high ledge followed by a 2.5 meter wide drainage canal need to have in order to land on the other side of the canal? Again, some wording issues. Oops, sorry. Hopefully we can move on with our lives. So, pictures. I think pictures are helpful. I think pictures are helpful. I think pictures are helpful. So, here's my shopping cart. Poor placement of where my shopping cart is. Here's my shopping cart. That is handled. It has a duo in it. So there's one person. Of course, you got to have the other person like, oh, going really fast. Okay, so then there is this drainage canal that has water in it, of course, because it wouldn't be much of a drainage canal if it didn't have water in it. And then just to, I don't know really why I do, but just to make it a little bit more intense, there are some spikes in this drainage canal. I'm not sure why to keep those. I don't know. I just like it. Okay, so the idea is we have a ledge that is 1.5 meters high. Red. So from here to here is 1.5 meters, from here to here. And from here to here is 2.5 meters. Well, what's going to happen is these people in their shopping cart are moving that way. And once they go off the edge of the cliff, they're going to go something like that. And they want to make sure they land on the other side of the drainage canal. Otherwise, see, now it's like there's a little bit bigger deal. Like, otherwise, it just get wet. It get wet and get poked and get like a sliver from that thing in their fingers. So that'd be bad. So they got to make it to the other side of the drainage canal, or else poke on their finger and ouch, that wouldn't be good. And what we're trying to ultimately determine is how fast will they have to move. So if we look at our problem type sheet, is this a 1D or is this a 2D motion? Hopefully we can all agree upon they're going to be moving through the air in 2 dimensions. Therefore, this is a 2D motion problem. So I'm trying to color code this for you. So because it's a 2D motion problem, then we make 2 lists of variables, and this is represented with my black marker. So we make a list for my x, a delta x, a vi x, a vf x, an ax, and a t. And is moving the y direction simultaneously, delta y, vi y, vf y, a y, and t. But because it's moving simultaneously through the air, my time in both the x and the y will be the same. The amount of time that it takes me to go from here to here is going to be the same time as it takes to go from here to here. That's all we're saying. So because this is a 2D motion problem, use the things I can write the things that I did in black. Then the next question, is it a projectile or a non-projectile? Those are really your 2 choices. So is the object moving freely through the air in 2 dimensions, or the people in the shopping cart, or are they not moving freely through the air? And the answer is, well, they are. So I think the way I have these is I say that my vix is equal to my vfx. So those 2 numbers are going to be the same, whatever the number is. And because my velocity is constant in the x direction, because there's no forces acting in the x direction, we can say that my acceleration in the x direction is going to be 0. We also know, because this is 2D motion, projectile motion problem, still with a green marker, that there is a force in the y direction. It's called gravity. The acceleration in the y direction is going to be negative g. And because we are on Earth, g has a value of negative 9.8 meters per second squared. Green marker. marker, because it's a 2D motion, projectile motion, it's either going to be a horizontal launch or an angle launch. So do they go off the ramp and then into the drainage canal, or do they just go off the edge of the canal? And the answer is, hopefully you can say, well, it doesn't say anything on ramp, it doesn't say anything about angle, so we're going to go with the horizontal launch. So because it's a horizontal launch, blue marker, we can say that my initial velocity in the y direction is going to be 0. Okay, black was because it's 2D. It's a special type of 2D motion problem called projectile motion, so we could put the things in black, the things in green on my list. Because it's a projectile motion, we have to ask ourselves, is it an angle launch or horizontal launch? Because it's a horizontal launch, blue marker, we could say my initial velocity in the y direction is 0, and we're kind of at the end of our list. Red marker out again for our problem type, so now we can pull numbers from our problem. And hopefully you're okay with saying, hey, up and down is my y direction, left and right is my x-axis. So then, hopefully you recognize that meters is displacement. So this is how far the cart moves in the x direction, so delta x is 2.5 meters. 2.5 meters. And from here to here is my displacement in the y. However, displacement's a vector. So we need to include a direction, and I'm going to use black just to kind of help make it stand out a little bit. My shopping cart goes down 1.5 meters, so therefore we need to have a negative 1.5 meters. It's going down 1.5 meters, therefore we need to have a displacement that is equal to negative, because it's going down, negative 1.5 meters. We're trying to figure out how fast they're going before they go off the edge of the cliff. We're trying to figure out what their initial velocity in the x direction is. That's our unknown. That's what we're going to be solving. If I give you time, then it really can be a one-step problem. If I don't give you time, chances are pretty good it's going to have to be a two-step problem. Because it's pretty typical we have to solve for time in the opposite column first, and then once we solve for it here, then we can plug it in the other column. And that's exactly what we're going to have to do here. There's only two numbers. We need three out of the four. So we don't have enough information in the x, so we have to start in the y. So we go through and we say, hey, I don't know final velocity. You didn't tell me how fast the shopping cart was going down right before it struck or landed. So we don't know that. And it's pretty common that we don't know that. So in the y direction, we're going to use equation number 3 because we don't have a final velocity. So in the y direction, delta y is equal to VIY times t plus 1/2 AY times t squared. So we're using equation number 3. Because my initial velocity in the y direction is 0, initial velocity in the y direction is 0, 0 times t is 0. Plugging in some numbers, delta y is negative 1.5, which is equal to 1/2 times negative 9.8 times t squared. And those are numbers directly from our list of variables. 1/2 times negative 9.8 is negative 4.9 t squared. So it's negative 1.5 is equal to negative 4.9 times t squared. We want to get t squared by itself. So we're going to divide by negative 4.9. We're going to divide by negative 4.9. Negative 1.5 divided by negative 4.9 is a positive 0.3061, blah, 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 blah. Lots of decimals. I'm going to be lazy and I'm only going to record 2 of the numbers. Now, when I do my calculation, I'm gonna use all of my numbers. I'm just gonna write down 2 of them. Now, is that my time? Is that t? No, that's t squared, right? So we need to take the square root of both sides. And I'm gonna take the square root of every single decimal point that my calculator gives me by going second, or the square root of my answer. And my t value is gonna be 0.553. So my time is 0.553. 3283335. Again, I'm gonna be lazy and I'm gonna record only 2 decimals. So I'm gonna record my time as only 2 decimals. Now if, and I will, if I need to use that time, I'm gonna use every digit that my calculator gave me once again to eliminate any rounding issues or any rounding. So now that we know the time in the y, we also know the time in the x direction. Now, part of my projectile motion problem said because my acceleration is 0, that we should use equation number 3 in the x direction. So we use equation number 3 a lot. It's not the only equation, but it's a pretty commonly used one. So in the x direction, equation number 3 is delta x is equal to vi times x, vix times t plus 1/2 times ax t squared. That's equation number 3. We simply added the x subscript to the initial velocity, the acceleration, to help show that it is specific to the x column. Notice how when I plug in these numbers, I am only using numbers from the columns. There is no crossing over. The acceleration in the x direction is never going to be negative g, because gravity never pulls things left and right. It only pulls down, and only in the y direction. So my initial velocity in the my acceleration in the x direction is 0, so my acceleration in the x direction is 0, so 0 times 1/2 is 0, times t squared is also going to have a value of 0. Now we're plugging numbers in for my equation. Delta x is 2.5. My vix is our unknown. My time is 0.55. Like I said, I'm lazy, so I'm only recording 2 decimals, but I have a whole string of them in my calculator, and I'm going to use them all. So I want to get vix by itself, so I divide both sides. By 0.55. So we're going to go 2.5 divided by, and again, I'm going to go divide by my answer, and my calculator will do that for me. And my vix is equal to 4.518. So because I say we can just round to 2 decimals, that's my final answer. So in order for my daring duo to make it across the drainage canal, they must be going a minimum of 4.52 meters per second. If they go faster, they're going to go further beyond. Okay, they're going 5 meters per second. Now they're not going to land here, they're going to land here. If they go 10 meters per second, they might land here. So the idea is, if we were to say what is the minimum speed that they must go, that's it. 4.52, we're good. 4.5 is like, oh, and I tipped in probably. Okay. That's the idea of these problems. General questions about these. All right, so on the way in, you grab the little half sheet. It's called the Progress Quiz 3.1. There's 2 problems, one in the front, one on the back. I have an answer key posted right here. I also have an answer key posted on that water jug on that table back there. Go through. If you want to do the first one, check it. Then do the second one, check it. Fine. If you want to do both, check it. I don't really care. It's kind of up to you on how you proceed with this. But I want you to check it. And if you have questions, I want you to ask those questions and get those questions taken care of and clarified. The sooner we take care of this, the better. Why? Well, here's the thing. Once you're done with those and you've checked those two problems, you can say, hey, Mr. Davies, I got the two problems done. Hey, nice job. I'm not recording it. This is just what we're doing. On that green chair over there is tomorrow's homework for your virtual day. You can get started on that problem. That's the second of 3 homework sheets for this 2D motion unit. So we're 2/3 of the way done after that of our homework sheets. They've all been horizontal launch problems. The one kind of next step is angled launch. We'll learn that next week. And then this unit's really over. We'll do a lab on Wednesday, horizontal launch off the lab tables. But our unit's pretty short. It's really just 1D motion, but we do it in both the X and the Y simultaneously. Okay, so progress quiz, get started on your homework with about 15 minutes left in class. So we're talking right around, we're down at 42, so right around, what is it, 25 after, right around 25 after. There's a half sheet also back there. It's got an Einstein meme on it. We will start and go on through that together as a class because it's going to be very similar to the lab that we're going to do on Wednesday or Thursday. Okay, so let me know what questions I can answer. If you look and say, yeah, I didn't get that, ask me. I'm here. Okay, so please make sure we get these things clarified. And then we'll come back and we will go through that in-class problem with the Einstein meme in a little bit. Editing. There. That's going to be amazing. All right, so we are taking a look at that little half sheet. It looks like this. It's linked in your in-person agenda. It's a problem that starts a teenager is driving. So a teenager is driving through the mountain on Kirby Road. They receive a Snapchat message and debate for a second as to whether they should read it or not. They remember the Wisconsin Department of Transportation campaign going on, better left on red than dead, but think that message is for old people who don't know how to use a phone. They decide to read it and they see a funny physics meme, of course it's going to be a physics meme, that they take their eyes off the road for just 1.6 seconds in order to respond to that Snapchat, or snap, I don't know, whatever. Yeah, that thing. I don't know what when you respond to it, you respond to a snap? Sure, Mr. Davies, you're old. I know. I'm feeling it right now, too. It's okay, though. In that short amount of time that took them to respond, they traveled 50 meters, and the road took a sharp turn, which they aren't able to make. But don't worry, because of airbags and good karma, they are fine. The cruise control is on, very conveniently, and the cliff is 30 meters high. How far away from the cliff do they land? So the idea is cliff 30 meters high, and they're going to go wee. And that was the airbag deploying, not the car blowing up. Was that noise? Maybe you couldn't even hear it through my mask. I don't know. This is similar to the lab we're going to do on Thursday. The lab we're going to do on Thursday, we're going to take that ramp, we're going to roll it through the photo gates, just like we did with 1D motion. But hopefully, you realize that when we rolled it 30, 30, 30, 40, 40, 40, 50, 50, 50, 60, 60, 60, 70, 70, 70, 80, 80, 80, 90, 90, 90 centimeters, their velocities were almost always the same. Smooth metal marble rolling across a smooth black surface lab table, very little friction, acceleration is essentially zero, velocities are constant. So we can use that same idea. And the idea is car drives down the road 50 meters in 1.6 seconds. Why is that important? What's that going to tell us? This is like through your photo gates, just for the record. Because from there we can go through and determine what? The velocity of the car, cruise control, very conveniently. Okay, they have their cruise control on. So from there we can go through and we can determine what their speed was when they drove off the cliff. This is a 1D motion problem. And this is only from here to here. This 50 has nothing to do with this 50. This 1.6 seconds has nothing to do with this. Okay? This is really a 1D motion problem. If we wanted to add our subscripts, we sure could. But 50 meters, cruise control, acceleration is 0, which means these are the same, and this was 1.6 seconds. From there, we could use equation number 3. We can say delta x is equal to VI times t plus 1/2 a t squared. Acceleration was 0. What we're left with is 50 is equal to VI times 1.6. My VI is going to equal 50 divided by 1.6. The car is moving at 31.25 meters per second. Because they had their cruise control on, it's going to be the same here as it is here, as it is here, as it is here, as it is here. Okay, that's how fast they're going to drive off the edge of the cliff. This is like marble on the table when we're talking about it. We can set up photo gates. We can measure a distance. We can time. We can measure a distance. We can time it. We can determine the speed at which my marble is going to roll off the table. That's a 1D motion problem. But this 50 has nothing to do with the projectile. This 1.6 seconds has nothing to do with the projectile motion problem of the car. Now we can go through and say, hey, now the car's going to go through the air. Is it a 1D or 2D? You bet it's a 2D motion problem. I heard every one of you screaming it. Okay, so because it's a 2D motion, black marker, we make 2 lists of variables. 2D motion, the car's going to be moving through the air. This is like the marble rolling off the table. We're going to let it go off the table. Projectile. Is it a projectile or not a projectile? Yeah. So these are the same because my acceleration is equal to 0 in the x direction. Because it's a projectile in the y direction. My acceleration in the y direction is negative g, which is equal to negative 9.8 meters per second squared. Do they go off a ramp, or do they just drive straight off the edge of the cliff? Blue marker. So therefore, it's a horizontal launch. Information from the problem. Red marker. 30 meters high, 31.25 meters per second, question mark. So how far away, delta x, question mark. How fast were they moving in the x direction as the car drove off the cliff? That was the cruise control. At 31.25 meters per second. And this is my delta y, but my car went down, so I have to put a negative, went down negative 30 meters. In terms of your lab, this is like the height of your table. This is the speed that we measure between your photo gates. This is how far from the edge of the table is it going to land. That's what we're calculating. So, pretty similar calculation that we've done thus far, where we have to go through and we have to solve for time in one column to then plug it into the next. Same thing here. Don't know final velocity in the y directions, never will. No, I shouldn't say never. We aren't going to calculate it. Okay, so that is our equation in the y direction. Because my initial velocity in the y direction is 0, that term cancels out. We're left with negative 30 is equal to 0. 1/2 negative 9.8 times t squared. Do something algebra, negative 30 is equal to negative 4.9 times t squared. Divide both sides by negative 4.9, divide both sides by negative 4.9, and then we get a value, 30 divided by 4.9, oops, 30 divided by 4.9. We get a value of 6.122, which is equal to t squared. I don't want t squared, I want t. Take the square root of both sides. T is equal to 2.474 seconds. Then once we get that number, we can plug it in there. So now we know that it takes 2.47 seconds for the car to drop 30 meters, which means it's going to take 2.46 seconds or 7 seconds to go to the right. And then we can plug this in, and we can plug it in here. In the end, just in terms of interest of time, in the x direction, we're going to use equation number 3. Delta x is equal to VIXT plus 1/2 AXT squared. Because my acceleration in the x direction is 0. When we go through and we solve for this, our final answer, I skipped all the algebra, is 77.32 meters, which is like is in the lab, it'll be from edge of the T. Because that's what we're going to be calculating, is how far should it land, and then we can actually measure how far does it. And that's the idea of these 2D motion problems. Again, we're kind of wrapping this thing up. We have to do Engelbach. They're a little tougher. We'll do those next week. We'll do this lab on Wednesday or Thursday. But we're going to be wrapping things up. So if you didn't understand this, again, it was on that little half sheet in the back, or it was linked in Canvas. If you have questions, please let me know. You want